This video gives us another opportunity to play around a little bit with Euler's method and connect it to something we saw in the previous section on slope fields where we talked about RC circuits. So let's refresh everyone's memory. So an RC circuit is going to have a voltage source, a resistor, and a capacitor. And we're going to be looking at the voltage across the capacitor. We're going to call that VC of t. Okay, so there's a voltage source, and essentially if you kind of remember what happened is, depending on here we had a 0 voltage source, then the voltage in the capacitor kind of exponentially decayed to 0. When we had a constant voltage source of 3, depending on where we started with voltage, again, the voltage kind of up across the capacitor exponentially approached the voltage source. And then we did more complicated things, like we could combine it in a piecewise function, right? The voltage exponentially approached the constant source, and then the source turned off, and the voltage across the capacitor exponentially approached 0, the new voltage source, right? So the kind of summary is that when we're looking at this RC circuit model that's governed by this differential equation right here, the voltage across the capacitor is exponentially approaching the voltage source, essentially, and that source may change over time. So as we're looking at one, let's go back to that governing equation, dVC dt. Again, VC is the voltage across the capacitor, and that's going to be the voltage source minus its current value. The rate of change of this voltage is going to relate to the voltage's current value. And that's going to be all divided by two constants, R and C. And we're going to look at a specific example so that we can actually use an algorithm. Specific example where R is 1/2, C is 1, and the voltage source is actually going to be periodic. It's going to be sinusoidal. And quick comment here, these are somewhat silly numbers that the textbook chooses to make things nice, but this would be a very large capacitor if we actually had values like this. So we're just kind of doing this to make things nice. And then the voltage source is going to be oscillating, right? Sine of 2 pi t is just a sine wave where a period is 1 unit of time. So we know that the voltage source is going to look like this. All right. So what is this going to kind of look like? When we plug everything in and simplify everything, it'll simplify down to something that looks like this, pretty nice. -2 times the voltage across the capacitor plus 2 times sine of 2 pi t. And that's going to be the rate of change. And we could do some qualitative analysis just like we did last quarter. We could say, okay, well, you know, this part is oscillating. This part is going to be kind of some exponential piece, like what's going to happen. But we're going to kind of skip that for now and just look at it with a numerical method. So let's play around. Maybe you have a computer program you wrote. Maybe you're working with Excel. Maybe you're doing it by hand. Maybe you have some program using from online. But if we look at our Excel and kind of implement this, again, using what we've done before, we're going to start, let's start at, I don't know, 0,3 or something. And our function, right, we just said our function was -2 times the function value. This is our derivative, right? It's -2 times VC. So maybe we could rename this so it's a little bit more accurate. Plus 2 times the sine of 2 times pi times the time, which is right here. And that, again, we'll want to drag that down. Oh my gosh. We're going to want to drag that down. And then things should be able to update. And then again, we're going to ignore this for now. So this is the voltage across the capacitor at time k. And oh, this is interesting. Look, we have some kind of exponential approach to something that looks a little sinusoidal. What if we have a different initial voltage level across the capacitor? Oh, it looks pretty similar. A smaller voltage, a smaller voltage. Oh, what if we start with a negative? You get the same thing, right? Like no matter where you start, you're kind of exponentially approaching that sine equation. It's kind of fun, okay? And you can see Euler's method creating our own graph. Like this, I'm not using any complicated program to generate this graph. This is literally, you saw me make this, right? You saw me make this in a previous video in about 2 minutes. And again, if we wanted a better approximation, we could change the delta t, but I'm not going to do that for now. But yeah, that's very cool. And we can compare this a little bit with, we could remember this slope field website that we talked about earlier. Remember to use it, you just go up here. You can use whatever variables you want. A lot of times we use y and t. We could say, okay, it's going to be -2 times, this is like y, right? Plus 2 times the sine of 2 times pi times t. Type that in, and let's make sure this is syncing. Let's, yeah, maybe 6 time cycles from 0 to, yeah, sure. And you can see that no matter where you start, oh, look at that, right? Depending, you're seeing that exact same behavior that we saw in our Excel model. So it's pretty cool, yeah. If we have a sinusoidal voltage source, again, it doesn't really matter where we start. We're kind of going to just kind of approach that voltage source in terms of what the voltage across the capacitor is going to look like. So we built this, right? We built this today using Euler's method, which is pretty cool. And you can see the same kind of behavior. We only plotted one at a time over here, but we saw, right, that you could change the initial voltage source. And we're getting all of those individual solutions that we're seeing here. So pretty cool. I think that's pretty much it for this video. The last video of this section, we're just going to talk about what can go wrong in numerical methods. And we're going to bring back a little qualitative analysis, but it should be fun. It should just be a nice, fun little summary thing. Yeah, well, until next time. Bye-bye.